semiconductor material we will discuss. So that means if you will take materials, so there are so many types of materials will be the insulators, conductors, semiconductors. So we'll discuss about the how they will classified. Okay. So based on the conductivity also we will discuss. So what is the conductivity? What is the conductivity? So conductivity means the ability of material to conduct the electrons through it. Okay, once again I will repeat, conductivity is nothing but the ability of material to conduct the electrons through it. That is called as conductivity. Okay, so understood what is the conductivity?
Yes, sir.
Yeah, so for different materials the ability will be different, and that means flow of electrons. So the ability of material to conduct the electrons through it annanga, so that means that is different for different materials. So based on those conductivity value, so the materials also classified. Okay, so like that semiconductors, conductors, insulators. Okay, based on the band theory of solids also we can classify. First of all we are discussing about the based on conductivity. Okay, suppose if you will take in case of semiconductors, the conductivity range is 10 to the power of minus 4 to 10 to the power of 4 Siemens per meter. Siemens per meter. So Siemens per meter is the units for conductivity. So Siemens per meter is the units for conductivity. Okay, here in case of semiconductors, what is the range means 10 to the power of minus 4 to 10 to the power of 4 Siemens per meter. Suppose if you will take insulator, that conductivity is less than 10 to the power of minus 4 Siemens per meter. In case of insulator, the conductivity range is less than, so 10 to the power of minus 4 Siemens per meter. If you will take what is that, conductors? Conductors are nothing but metals. So all metals will behave as a conductors. So in case of conductors, what is the conductivity range means? So greater than 10 to the power of 4. Greater than 10 to the power of 4. Okay. So that means if you will observe the semiconductors, so the conductivity range is in between the metals and insulators. The range of the conductivity is in between the metals and insulators. Metals and insulators. Okay. Now the interesting feature about the semiconductor is that they are bipolar and the current is transported by two types of charge carriers of opposite sign. Okay, so but if you will take in conductors, conductors means how charge will flow in case of conductors. So due to the motion of the electrons, due to the motion of the electrons, that means their conductors are monopolars. That means only one type of charge carriers will be there. But in case of semiconductors, bipolar. That means what is the meaning? The bipolar means, so there are two types of charge carriers will be there. So what are those two types means? So first one is the electrons, second one is the holes. So through holes current will passing here, and through electrons also current passing here. Okay, so due to that, so what happened here? So current is, that's why we will call it as semiconductors are bipolar. Okay, so that means in these semiconductors current is passing due to electrons as well as holes. Okay, so now coming to the based on the band theory of solids, based on the band theory of solids, how these materials are classified. So before we discussed, so based on the conductivity, here based on the band theory of the solids. Okay, so if you will take any material, that material contains so many number of atoms, okay. Suppose see here, so here two atoms will be there. So inside nucleus, outside electrons are revolving, so that means those two atoms are, so that means I have different atoms here. Suppose so this, if you will take this atom having E1 energy, this atom having E2 energy. Okay, that means those energy levels will be E1 and E2 like that. If you will take the three atoms here, so here, so those electrons will be there. Electrons are revolving, so those electrons energy levels E1, E2, E3. Okay, so that means those electrons energy levels combinedly form. Suppose if you will take n atoms, so these all energy levels are combinedly form one band. That means, so in that band, so many energy levels will be there. So there is a energy band gap. This is the energy band. Okay. this in that energy band, so many energy levels will be there. See here. So n energy levels are there. N energy levels are there. So that means, so if you will take any material, there are so many number of atoms will be there. So in that atom, so many electrons are revolving. Electrons are revolving. So though according to the band theory, I am saying this. Okay, according to the band theory of solids, I am saying, so many atoms will be there. Those are around that atoms, electrons will be revolving. So those electrons, each electron have particular energy levels. Those all energy level combinedly form one band. One band. Okay, that is the band here. Okay, now we will discuss. See here. So outer, that means if you will take atom, there are outermost electrons will be there, innermost electrons also there. If you will take any atom, so there are innermost electrons are there, outermost electrons is there. That means some electrons are rotating outer cells. Suppose if you will take yeah, here n equal to 1, n equal to 1 means, so these electrons are inside, these electrons are inside, so n equal to also inside. So what is the here outermost electrons? So if you will take n equal to 3, n equal to 3, that means in that n equal to 3, suppose previously we discussed now so many number of electrons. So that means in that so many number of electrons combinedly form like a band. Okay, so like this band, in this band. So these band, that means outermost electrons combinedly form one band. Okay, so that band we will call it as valency band. Valency band. So in this valency band, so electrons have that means if you give outermost, this means these electrons are outermost electrons. That's why these are loosely bound with the nucleus. These electrons are loosely bound with the nucleus. That's why if you give little energy also, if you give little energy also, so these will become free. These will become free from the nucleus. Free from the nucleus. That means if you give little energy of the these electrons, what happen means, so they escape from the what is that nucleus bonding. Nucleus bonding. Okay, so that's why those electrons will become free. So those electrons will not come out from the material. Those electrons will not come out from the material, but so those electrons escape from the nucleus. What is that attraction force? Nucleus attraction force. So that's why those electrons will move freely inside. Freely inside. Okay. So see here, so like that, so inside electrons it will be there, outside electrons will be there. So the attraction between the nucleus and so these electrons, attraction between the nucleus and these electrons are so very small. If you give little energy also, what happen, it will free from the nucleus, it will free from the nucleus. So that's why those electrons will move freely entire the material. So those electrons freely move from the entire material. So due to those electrons only, what happen, conduction will be takes place. Due to those electrons only, conduction will be takes place. So here, so suppose if you give little amount of energy to this electron, those electrons free to move inside the atom. So those can move from here to here. So suppose if the nuclear force will be there means, so only electrons rotating around the nucleus. Okay, but so if you that those electrons, outer cell electrons, we will call it as valency electrons. Those valency electrons have loosely bond with the nucleus. If you give little amount of energy, what happen? It will become free. It will move inside the material. Okay. So due to that motion, what happen? Conduction will be takes place. Due to that motion, conduction will be takes place. Okay. So whatever the electrons in the conduction band, so involving in the conduction, so those electrons we will call it as conducting electrons. So which electrons participates in the conducting process, those electrons we will call it as conducting electrons. So those electrons energy combinedly form like a one band. Those band we will call it as conduction band. Okay, so valency band is nothing but So outermost electrons, if you will take any atom, all outermost electrons combinedly form, okay, combinedly form a one band. That band we will call it as valency band. Valency band. If you give little energy to that valency band, what happen? They will become free. Those valence electrons will become free. It will move entire the atom. So that's why what happen? Conduction will be takes place due to that electrons. So those electrons occupy some energy. So those energy we will call it as conduction band. Conduction band. Okay. So this is about the valency band and conduction band. So there is a energy gap between the valency band and conduction band. Okay. That is the energy band gap. Energy difference between the valency band and conduction band. So that is called as, what is that? Energy band gap. So based on the energy band gap, so based on the, suppose if you will take here, so this is the conduction band, this is the valency band. Suppose if you will take, so if you observe here, there is a energy band gap between the valency band and conduction band. If you give little amount of energy here, so what happens? These electrons will jump from valency band to conduction band. Okay. Now based on this band gap, based on the this valency band and conduction band, that means based on this band gap, so materials are classified into insulators, conductors, semiconductors. Okay. So what is the conductors? Conductors means, so these valency band and conduction band both overlap with each other. Valency band and conduction band both overlap with each other. That means there is no energy gap. There is no energy gap between the valency band and conduction band. That's why what happened in case of conductors? In case of conductors, so without giving any energy, so those will act as a conductors. So if you will take any metal, there are so many number of free electrons will be there. So those free electrons, without giving any external energy, so those will move from one side to another side. If you apply the potential, what happen? All electrons will move from particular direction. That's why there is a current passing through the conductors. Okay. Now coming to the, in case of insulators, so these energy gap is, that means energy gap between the valency band and conduction band is small, very small. So that means if you will take germanium, 0.7 electron volts. If you will take silicon, okay, so silicon, so that is 1.21 electron volts. That means in case of semiconductors, that energy gap is less than 3 electron volts. In case of semiconductors, so the energy gap is so less than 3 electron volts. If the energy gap between the valency band and conduction band is greater than 3 electron volts, means those we will call it as insulators. Okay. So if you will take the conductors, what is the energy gap? There is no energy gap between the valency band and conduction band in case of conductors, because both are overlap with each other. In case of semiconductors, what is the energy gap? Energy gap means, so 0 to 3 electron volts. Suppose if you will take example germanium, 0.7 electron volts. If you will take silicon, 1.21 electron volts. Okay. Now coming to the, in case of insulators, what is the energy gap? Means greater than 3 electron volts. Okay. So based on the band gap here, so materials are classified into, again, so here 3 types. Okay. So those are already we discussed. Okay. So any doubt on this and valency band and conduction band, students? Okay. Now,
No, sir.
okay. Okay. Yeah. So here this is about the valency band and conduction band. Okay. Now, so already we discussed what is the semiconductors here. Semiconductors means, so the energy band gap is less than 3 electron volts. 0 to, so less than 3 electron volts. Those materials we are called as, so semiconductors. Those conductivity, what is the conductivity range of semiconductors? 10 to the power of -4 to 10 to the power of +4 Siemens per meter. meter. That is the conductivity range of semiconductors. Conductivity range of semiconductors. Okay. Now coming to these semiconductors. These semiconductors are classified into two types. These semiconductors are classified into here two types. One is the intrinsic semiconductor or pure semiconductor. Pure semiconductor. Another one is the extrinsic semiconductor. Extrinsic semiconductor. So those we will call it as impure semiconductors. Intrinsic semiconductors are nothing but pure semiconductor. Extrinsic semiconductors are nothing but impure semiconductors. Impure semiconductors. Again, extrinsic semiconductors are divided into two categories. So one is the depends on their doping percentage. Depends on their doping percentage. Doping element depends on their doping element. So again, extrinsic semiconductors are classified into two types. One is the p-type semiconductor. Another one is the n-type semiconductor. Okay. So we will discuss about the p-type and n-type later. First of all, we will go through the intrinsics or pure semiconductor. Okay, so in case of intrinsic semiconductor, there is no doping element will be there. There is no doping. Okay, so now here, suppose what is the example for intrinsic semiconductors? So silicon and germanium we discussed. Okay, silicon and germanium. That means all fourth group elements. So fourth group elements are the best example for intrinsic semiconductors. Fourth group elements are the best example for intrinsic semiconductors. Okay. Yeah. So here one more thing is there, Fermi level. Fermi level. So what is so that means this is the valency band and this is the conduction band. Valency band and conduction band here. So first we will discuss about the Fermi level, then we will go for the intrinsic semiconductor deeply. Okay, so now see here, that means at lower temperature. At lower temperature means absolute temperature. Absolute temperature. So there is no electrons in conduction band. If you will take either metals or semiconductors, anything. So there is a so maximum energy of electrons. There is a maximum energy of electrons at absolute temperature. There is a maximum energy of the electrons at absolute temperature. So that maximum energy we will call it as Fermi level. Fermi level. So that means, so at absolute temperature, if you take that, so whatever the electron will be there, that electron energy is less than the energy of the Fermi level only. Those electron energies less than the energy of the Fermi level only. So that means this is the maximum level. Maximum level. That means no more electrons. So greater than that much of energy. No more electrons greater than that much of energy at absolute temperatures. At absolute temperature. That means, so maximum energy occupied by the electron at the absolute temperature, we will call it as Fermi level or Fermi energy level. Fermi level or Fermi energy level. Okay. So this is about the Fermi level. Okay. First of all, we discussed about the intrinsic semiconductor. Okay. Intrinsic semiconductor. A semiconductor which does not have any kind of impurities. Any kind of impurities behave as an insulator at absolute temperature. Absolute temperature is nothing but 0 kelvins. 0 kelvins. And behave as a conductor at higher temperature is known as intrinsic semiconductor or pure semiconductor. Once again, I will repeat, a semiconductor which does not have any kind of impurities. Any kind of impurities and behave as a insulator at 0 Kelvin. 0 Kelvin. 0 Kelvin is nothing but absolute temperature. And behave as a conductor at higher temperature is known as intrinsic semiconductor or pure semiconductor. Okay. So now example of the intrinsic semiconductor are germanium and silicon. And all fourth group elements. All fourth group elements are the best example for intrinsic semiconductor, and they possesses diamond cubic crystalline structure. So their structure will be so like a diamond cubic crystalline structure. Okay, how they will get the diamond cubic crystalline structure, I will explain you. So if you will take silicon, so what is the valency electrons of silicon means? So there are 4 valency electrons will be there. Silicon have, so 4 valency electrons is there. Okay, so those valence electrons having sp3 configuration, sp3 configuration. Okay, so that means for fulfilling that, those will have 6 electrons. Those will, so that means outermost, suppose what is the stability? So every element try to get the stability. Every element try to get the stability. Stability of atom means how they will get the stability means, so if they fulfill their shells, so their outermost cell, so they will get stable, they will get stable. Either so they try to lose the electrons, either they will try to absorb the electrons. So they will try to absorb the electrons, they will try to lose the electrons. So that's why what happened, they will try to bond with the surrounding atoms. They will try to bond with surrounding atoms. So similarly in case of silicon also, in case of silicon also, so depends on different metals, bonding will be different. Suppose if you will take semiconductors means, so the bonding between the atoms is what is that, covalent bonding. There are so many types of bondings will be there: ionic bonding, what is that, metallic bonding, covalent bonding, so many will be there. So here in case of semiconductors, in case of semiconductors, there are outermost electrons are, so 4 electrons will be there, outermost cell 4 electrons will be there. For getting the full stability of the electrons, it requires 6 electrons, it requires 6 electrons. So because p orbital so contains total 6 electrons, so that means silicon having, so outermost cells is a p orbital, so there are four electrons will be there. So for getting the stability means it requires 2 more electrons. So that's why, so here, so what they will do means, so they bond with the surrounding atoms, they bond with the surrounding atoms. Okay, suppose this silicon atom I am taking, so this silicon atom having 4 electrons, so that means it's bonding with the, so this electron as well as this electron. So that means, so this electrons, 1 electron here, if you observe here, okay, so this is have only 4 electrons, but here is showing, so that means one more electron, 5 electrons is showing. So how it will be means, for getting the stability, so 1 electron shared with the, so neighbor atoms, electrons shared with the neighbor atoms here. So that means these two electrons are combinedly shared with this silicon and this silicon, this silicon and this silicon. Similarly, so this surrounding silicon also combinedly shared with this electron and this electron to the, so both combinedly share the both silicon atoms. That's why, so what happened, covalent bond will occur between the silicon atoms. Similarly, if you will take any electron, so that is covalent bond occur between the surrounding silicon atoms. Okay, silicon and germanium are the elemental semiconductors, and they have 4 valence electrons which are distributed among the outermost s and p orbitals. These outermost s and p orbitals of semiconductor involve sp3 hybridization. Okay, so these sp3 orbitals from 4 covalent bonds of equal angular separation and leading to tetrahedral arrangement of atoms in space results tetrahedron shape. Okay, so because of the this bonding between the surrounding atoms, what happened here, tetrahedron shape will be occur, tetrahedron shape will be occur. So resulting crystal structure is known as, so diamond cubic structure, diamond cubic crystal structure. See here, so this is the tetrahedron shape, tetrahedron structure. Okay, so that's, so these tetrahedron structure, so if you will take in 3 dimension unit cell, so it will be, so diamond cubic structure, diamond cubic structure. Okay, that is about the, so what is that, structure of the silicon atom. Similarly germanium atom also same. Okay, it's outermost have, um, what is that, 4 electrons will be there. So for getting the stability, so what happened, it will covalent bond with the surrounding atoms. Okay, yeah. Now coming to the carrier concentration in intrinsic semiconductor. Carrier concentration in intrinsic semiconductor. So when a suitable form of energy is supplied to the semiconductor, then the electrons take transition from valency band to conduction band. Okay, so in case of what is that semiconductor, so we will discuss before. So what will happen, there is a valency band will be there and conduction band will be there. So at lower temperature there is no more electrons at conduction band. Okay, all electrons occupy the valency band at lower temperature. So now if you give the some energy, to the so valency band electrons, valency band is nothing but outermost cell electrons. Valency band is nothing but outermost cell electrons. Okay, so if you give little amount of energy to the valency band electrons, what happen? They will move from valency band to conduction band. So conduction band is nothing but so those electrons involving in a conduction process. Those electrons involved in a conduction process. Those electrons we will call it as conducting electrons. So their energy we will call it as conduction band. Okay. So what happen means in case of silicon, if you give little amount of energy, so what happen? Those electron will jump from so valency band to conduction band. Okay. So hence a free electron in conduction band and simultaneously free hole in valency band is formed. Okay, so that means from that valency band, what happen if you give little amount of energy means so those electron is jump from valency band to conduction band. So if electron is jumping means in the place of electron, so one hole will be formed. Okay, so that means what happened here? So if electron is jumping from valency band to conduction band, so electrons will be so present in a conduction band, holes will be formed in a valence band, electrons will be present in a conduction band. Okay, conduction band. So this phenomena is known as electron hole pair generation. Okay, now coming to the in case of intrinsic semiconductor. Intrinsic semiconductors means pure semiconductors. The number of conduction, the free electron, the number of conduction electrons. That means conduction band, how many number of atoms will be there. Okay, so in intrinsic semiconductor, the number of conduction or free electrons will be equal to the number of electrons vacant sites or holes. So electron vacant site is nothing but so if electron is jumping from valency band to conduction band means so there is a vacant site occurring a valency band. So those vacant site we will call it as a hole. Okay, in case of intrinsic semiconductor, so number of electrons in a conduction band is equal to the number of holes in a valency band. What is the reason means? So if electron is jump means holes will be formed. Okay, that's why. So how many electrons are jump to the conduction band? So that is equal to the number of vacant sites. That means that both are equal. In case of intrinsic semiconductor. That's why number of electrons in conduction band is equal to number of holes in valency band. Okay, so now observe here. So this is the conduction band, this is the valency band here. See here. So here how many electrons will be there? That much of holes will be present here. Okay, so now in case of valency band, so that is only in conduction band only electrons will be present, but in case of valency band holes will be present as well as electrons will be present. Okay, so now observe here. So kinetic energy of the electron means so total energy of the electron is kinetic energy plus potential energy. So potential energy depends on the position. So what is the position here? So conduction band. So that means so the EC gives the position. So what is the energy of the conduction band? That is the position here. Okay, so due to the position some energy occurs. That is the what's that potential energy. So here, so those electrons will be in conduction band. That's why what is the potential energy of that? That means EC is the potential energy. So what is the kinetic energy? Kinetic energy is the, suppose this electron is having energy E, total energy E. So kinetic energy of the electronic K equal to so E minus EC. Similarly here also, so what is the potential energy? EV is the potential energy. So kinetic energy of the hole is here. So EV minus E. So this is about the conduction and valency band and its electrons. Okay, so yeah, it's time up. So now I will take the attendance first.